So, obviously, we went through the notes about the testing a hypothesis. So, we're going to be kind of working through this first example, pretty, specifically working through each of these little steps that we have and, coming up with, a good conclusion. Some of the other ones, obviously, they won't be necessarily as in-depth. We'll still answer the questions, but it won't be to this level. So, is there a home field advantage in baseball? In 2007, the home team won 54.26% of 2,431 games. Is this due to natural sampling variability, or is it evidence that there really is home field advantage? All right, so I'm going to try to for the hypothesis, write in words, and then also write mathematically what we're looking for. So, I don't like that color, purple. All right, so basically our hypothesis, we assume that there's no change. So we're going to assume, specifically for this problem, there is no advantage. And P is the proportion of games won. So we're going to have our null in our alternative hypothesis. So the null is that there's no change. So if there is no home field advantage or disadvantage, however you want to think about it, then our win percentage should be exactly 50-50. Basically 50% of the time you win, 50% of the time you lose. So this would mean that,
right?
yeah, okay. P equals 0.50. Let me try to, there. Make it a little easier to read. Kind of just all flows together. So, like I said, sometimes, excuse me, there's going to be, a specific, phrasing or wording or something that causes us to know if we're doing right tail, left tail, or two tail test. But they said home field advantage, which knowing just a little bit about baseball would mean that you have to win more than you lose. So, kind of the key thing here I'm looking at is home field advantage to give me the clue in that I'm using greater than. So it's going to be P is greater than 0.50, which this just means that the home team wins more often. Wins more than loses. And typically, you don't need to write this extra stuff that's, written out. This is just so that as you go back, you see exactly where we're getting all of our information from. So, our model, which is going to kind of be where we check our conditions to make sure that everything is meeting the necessary requirements. So we're obviously doing the conditions of a normal model. So independence. So this one is, in this case, relatively true. Obviously, right now we only have data on one season. Okay, so it's kind of hard to say for sure, but the seasons, while they're different seasons, are similar to each other. And obviously every team is different from each other, so I would say it's independent. So seasons, similar to each other. And one team doesn't affect the other. In the sense that, because that could be a little misleading the way I've written that, but, in the sense that a team winning in Cincinnati doesn't affect another game going on in Atlanta. Obviously, one team has to win and one team has to lose in one particular stadium. That's just the way it works. But as far as like each individual game is, I guess I should say maybe one game doesn't affect the other might be a better way to say it so that it's not confusing. As far as randomization, I mean, obviously, there is a little bit of randomness to the games and when they happen, who you play, and all of that, because a baseball team plays, I think it's 162 games. So, obviously, there's a little bit of random, but also at the same time, you have to play the people in your, like, immediate conference, which is not what they call it, I don't think. But anyways, but you have to play them so many times, home and away, and stuff like that. So, while it may not be randomly selected, it's definitely representative because we're looking at all the teams. So, not randomly selected. But representative. The 10% condition, 2,431 games or less than 10% of all games played ever played. Then success failure, N times P is 0.5 times 2,431, which is 1,215.5. And NQ is also going to be that because we used, oops, that's not a Q, that's a G. The same numbers, 0.5, obviously. It's going to be the same thing. So both of these are greater than 10. So we're good. So we can use the normal model. And one prop Z test.
Did anyone else see that?
Yes.
Okay, good. That like flash of light.
I know, I was like, that's sometimes what I see when I'm about to get a migraine, so I was like, please tell me somebody else saw that too.
Blink when it happened?
Well, it was behind you.
Oh, that might be.
It was like that light back there.
Okay.
So I was like, whoa.
What was that?
I was like, I hope somebody else saw that. And I looked up and y'all were all like looking around. I was like, oh, good.
It looked like, you know, like when sometimes your phone, like if you're holding it and then it'll like all of a sudden catch something and like show
Yeah.
up. It looked like something like that. I was like, whoa.
This light right here has something wrong with it, but I'm pretty sure it was that backlight. I don't really know though.
I don't even know.
I was just like, oh dear, that's not good.
No. Getting flashbacks from like a few days ago.
Alright, so the mechanics, this is where we actually do the math of the problem. So, mu is P sub 0, which is 0.5. So obviously this is what we're expecting, or like what in theory should happen, that there's no change, anything. So this is from the null. Which again, you wouldn't have to write that, but just for if you go back and look. The standard deviation of p hat is the square root of p sub 0 q sub 0 over n. So this is 0.5 times 0.5 divided by 2,431, obviously all under the square root. Not that button. And I get 0.0101 Now, I'm going to run the one prop Z test on this, which I may not technically need the standard deviation in this particular problem, but sometimes we need it. So, let's see if this color shows up. Yeah, it does. So, one prop Z test. So that's under stat test. One prop Z test is option 5, in case you want to write that down. So we've got 0.5. So it's our P sub 0 is the first number. Then I've got X, which in our case was, whose is that?
I guess it's yours.
I haven't given anybody glue.
Okay, Shane, go glue apparently. You stole it.
I don't even have glue like that, so I don't know where that came from.
Oh well.
Wait, doesn't Miss Patton have glue like that?
Yeah.
You give it to the wrong room?
It's possible. I don't know. We'll figure it out. All right, now, in the X, it has to be a whole number, okay? But the number that I'm going to get this from is 0.5426, which is...
Open a parentheses in the parentheses.
I am, but just for a minute. So, is this number up here that's a percent as a decimal, okay? So I'm multiplying. The reason I did this is because I'm doing that times 2,431, which if I type that in, it's going to put it, hold on, let me go back up here and show you. I'm going to show you what happens. All right, so, well, actually, hold on. Let me finish putting in what we need to put in. Our N is 2,431, and we know it's a greater than, so we're using greater than P0. And that'll be the option that we select. All right, so if I type in, which you can't really read now, but the numbers that I multiplied in here, the 0.5426 times 2431, what you're going to notice is it gives me a decimal. So you can wait and multiply it in here, or you can multiply it and then type just the number in. But it's got to be a whole number, because if I type it in with this decimal, I'm just going to show you what happens so you see. It's going to come up and tell you there's a domain error because it's got to be a whole number. So if I go back, though, and I delete off the decimals, everything else stays the same. Now it produces an answer. So if you ever get a domain error, it's probably because you put a decimal in that's not supposed to be. The only thing that can be a decimal in what we typed in is the p-value, the p sub 0. So I usually note when I do this that this is 1319. So that's why I did put a parentheses in there this time. Normally I will go ahead and multiply the number off to the side and then just put in the whole number. So from here, the number that I'm looking for, I get a z value of 4.2. And what? P is 0.00013, blah, 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 blah. Keeps going. Now, I could use the z-table thing and find this also, but now, we're in a normal model. That's essentially telling me I'm 4 standard deviations away, which is obviously very far away, so this number does not surprise me at all that it's so small. Okay, so to conclude this problem, we would say something like a p-value of less than, and this is just in general 0.001 because that's 1%, says that if there was no home field advantage, and the true proportion of home wins was P equals 0.5, then the observed value of 0.5426 or larger would occur less than because the number that I got basically less than 1 out of 10,000 times. And I really probably should actually use the p-value here that I got, the 0.0001. Wait, this needs another 0. This is supposed to be 100,000. Have a little typo there. So less than 1 out of 100,000 times this would happen. So specifically the part that we're really looking for here, so I'm going to write this on a new line. This would be the key part that we need to say. A p-value that small would cause me to reject the null hypothesis and shows that there appears to be enough evidence of home field advantage. So that part there that I just highlighted is the key part that we've got to have. I reject the null, and so there essentially appears to be or is enough evidence of home field advantage. Now, I think I mentioned yesterday that sometimes it's good for us to also find a confidence interval to see how confident we are, essentially, that this is the true proportion. So if I did that with this data, and what's really cool is that because this information was in a 1-prop-Z test, when I go here to stat test and I go up to 1-prop-Z interval, it actually takes those numbers over that I've already input for X and N from the previous thing. The only thing that may have to change is confidence level. So I would say maybe do either a 90 or a 95 confidence level. Really doesn't make a difference for this particular problem, but I'm just going to go with 95 because that's what's here. And we calculate, and this is going to give me a confidence interval here for that. And so my concluding statement that deals with that would say something like, if we create a 95% confidence interval with this data, we get, and it was 0.523 to 0.562 for the true proportion of home team wins. So that basically is saying between 52.3% and 56.2% of the time, we're going to see that the home team wins. Basically. Now, if they don't ask you for that, obviously we don't necessarily have to write that. This problem didn't specify, but I just thought it was good to have that so we see how it can kind of tie everything together here. All right. All right, so this next question, not as much math involved. We're actually just setting up the different hypothesis. It just wants us to write the null and alternative hypothesis for each situation given. So we test a new flavor of soft drink, planning to market it only if we are sure that over 60% of the people like the flavor. Okay, so keyword here in this one is over 60%. So my null hypothesis is that P is equal to 0.6 or 0.60, however you want to do it. Because that's that there's no change at all. Then it says over 60%. So what does that imply? Does that imply that it's greater than, less than, or not equal to for the alternate?
Less than. Wait.
Over 60%.
Oh, so more than.
Yeah. So greater than, so P is greater than 0.60. And so this would be a right tail test. Which it's not asking us to write that, but it's just good to go ahead and note that to start getting that in our minds of which way it is. All right, let's see the next one. 20% of cars of a certain model have needed costly transmission work after being driven between 50,000 and 100,000 miles. The manufacturer hopes that a redesign of a transmission component has solved this problem. So, what is our null here?
20?
Yep. Now, this one I will say the wording of it's a little bit more difficult, but this tells us that the manufacturer hopes that a redesign of the transmission component has solved the problem. So, that would mean what?
Like, they're using the, like...
Or what are they hoping that the result is going to be by that occurring? Them
Over
redesign.
20%?
Huh?
Over 20? Wait.
So right
Less
now,
than
20% have a problem. So yes,
Less than 20%.
yep, they're hoping that the redesign, so you're kind of having to infer a little bit, is going to resolve that issue so it's less than 20%. So that means that my null then, or sorry, my alternate is P is less than 0.20. So this one would be a left tail test.
Wait, so HO is the null?
The null,
right?
yeah.
And then HA is the what again?
It's called alternative, but I usually just end up saying
Alternate.
alternate because it's just alternative is just, I don't know, a harder
Too
word to
long.
say.
Yeah.
All right, in the 1950s, only about 40% of high school graduates went on to college. Has the percentage changed? So what is our null?
Oh, you're covering 50? What, 40?
Yep. 0.40. Now, keywords here are, has this percentage changed? What would that make our alternate?
Could be. Is it one of those like greater or less than or equal to?
So change just implies that it can't be 40.
So. Oh, equal with like the little line?
The equal with the line through it, so P is not equal to 0.40. So this means that this one is a two-tail test.
Oh, that line. I was saying the little squiggly line.
I was about to say, I was like, what?
Yeah.
Congruent?
Yeah.
I was thinking you were saying like, is approximately equal to or something.
Oh.
Yeah.
I was
Yeah, no.
confused.
Our options are greater than, less than, or not equal to. There's no less than or equal to, no greater than or equal to.
How do we do that though? Because if we don't know if it's actually changed or not, like imagine it was just still like 40%. Like why do we infer that it's just like not equal?
Well, change would mean it could be 39.9% or it could be 40.1%. Like, I mean, it could be anything in there. It could be
Right.
98% go to college now. I mean, it's changed is just saying it's not equal to that, but it could be anything
But if it's
earlier
like
or
asking
after.
us if it's changed, like how do does that work? Like the word for in that. Just the fact that it has the word changed in it.
That it's changed. Like the other ones have said, like it's like a redesign, which implies that it's got to be less than. You're having less than 20% of people with a problem.
Okay.
Or the other one said over 60%. That one implies.
Right.
So it's going to be a key word that's going to tell you it's either less than or greater than, or a key phrase there. Whereas this one, if you see the word changed, if it just says has changed or anything like that, it 98% of the time is going to be not equal to. There's going to be something else with the changed if it's going to be greater than or less than. It's going to have to say something else like that's going to imply that it's that. So, all right, this next one is a multiple choice question. So, the seller of a loaded die claims that it will favor 6, but we don't believe their claim, and we roll the die 200 times to test an appropriate hypothesis. Our p-value turns out to be 0.03. Which conclusion is appropriate? Look through that for a second and see if you can take a guess.
I really
I
don't
have
know.
a guess. I don't know if it's right, but I have a guess.
What's your guess?
D.
You think it's D?
Maybe.
Chris, if this was on the AP exam and you have 30 seconds to answer it left, what answer are you gonna pick?
I'm gonna say A. I'm gonna go with A, but it feels too easy, so I don't know. But I'm just gonna go with A.
You're gonna say
I'm gonna say A. I don't
A?
think
Alright,
that's right.
so.
I'm failing the exam.
Alright, so our p-value here is 0.03.
Right.
So this is basically what we're looking at is the probability of our sample results given that the null is true. So the null for a typical dice would be what?
6.0. Wait. 0.6. Wait. What am I doing?
So this says that it favors the number 6. How many numbers are on a dice?
6.
6. Okay, so that would mean that my p should be 1 over 6, which is equal to 0.17. So this is the probability that the dice is fair.
I knew there was a 6 in there.
So if it favors a 6, what does that mean about my probability? That means that the 6 is rolled more often than it's not. The 6 is rolled more
So
times
greater
than
than.
it's not.
There we go.
So this is the probability of greater than 1 over 6 or greater than
I
0.17.
thought you'd like already answered the question.
So this is that the die is unfair and favors 6. So what we say is that when P is low, we reject the null hypothesis. So P sub 0 equal, or P equal to 0.03 is low. So reject the null in favor of the alternative. So that means that the answer is D.